This is joint work with Arun Sai Sugala, Karthik Gupta, Adarsh Prasad, and Pradeep Ravikumar, all of them from CMU. So the minimax estimation problem is one of the fundamental problems in statistics. Let's say we have a family of probability distributions p theta, parameterized by this parameter theta, which lies in some set, and we are given n samples from some one of the distributions here, p theta star, so corresponding to the parameter theta star. So the task is that we are given x1 to xn, which are sampled from this theta star thing, and we need to estimate theta star from these samples. Okay. Mathematically, we would write it as minimizing over all the estimators theta hat, which take in the samples and then output a parameter vector, and then we wish to minimize the error between the theta hat of x1 to xn minus theta star, and then the expectation is over the samples coming from theta star. Okay. Now, a trivial solution to this would be just output theta star, irrespective of what the samples are, but the thing is we don't know what theta star is. So the right way to actually write this is to minimize not just this by fixing theta star, but rather to minimize this function where theta is unknown. So in order to put that, we take a max over theta. Okay. So we want to minimize over all the possible estimators the function where we wish to look at the worst case loss that our estimator suffers, meaning that for I'll pick the worst case theta and then try to maximize. So given an estimator theta hat, I'll pick the theta that maximizes this error. So that's the worst case risk of the estimator that I have, and then I want to minimize this worst case risk, and then I want to do this minimization over all the estimators theta hat. Okay. And this is a extremely well studied topic in statistics, and there are like these books on these topics. While this seems quite simple in some sense, it's not. It's also kind of unintuitive sometimes. So let's just take a simple example. So let's say I get a single sample from a Gaussian distribution with mean theta, and standard the covariance matrix is identity. Okay. So I give you just a single sample, and I want to get an estimate of theta just based on this single sample. So any guesses on what the answer is? I give you a single sample from a Gaussian distribution, and I want you to tell me the estimate of the mean of that distribution. Sorry? Yeah, so it turns out that the sample itself is not good, and there is this estimator known as the James Stein estimator, which essentially returns the direction of the sample, but then when d is greater, so d here is the dimension of the data. Okay, so when d is greater than or equal, so d is less than or equal to 2, you just return the sample x itself. But when d, the dimension is greater than or equal to 3, you return a scaled down version of the sample. And it turns out that this is pointwise better than returning the sample itself, meaning that this risk for any theta, the risk of this is better than just returning the sample itself. Okay, so while this seems like a very trivial problem, it could also be very counterintuitive in certain settings. Okay. So the rest of this talk, the outline is as follows. I'll first give you some more background about how to solve. So broadly, I want to solve minimax problems of this sort, right? So I'll first give you a background on what do we know about how to solve these minimax problems. Then I'll briefly make a connection to online learning and see how we can solve minimax problems using online learning, but we'll not go into details at this point. And then I'll first present the non-convex online learning setting and then algorithm for the setting. Then I'll give more details about, once we know how efficient algorithms for doing this, how do we use this to do the minimax estimation in order to solve problems of this form. And then in the third part, I'll explicitly instantiate this framework for the simple setting of constructing a minimax estimator for Gaussian mean estimation. Okay. So this is outlined. So let me first start with the background. In general, so the minimax optimization framework is that we have two sets of parameters theta hat and theta, and I have a function L. I want to minimize with respect to theta hat, and then I want to maximize with respect to theta. Okay, this is the general minimax optimization problem, and historically this has been extremely well studied when the function L is convex in the minimization variable theta hat and concave in the maximization variable theta. Okay, so if the function is convex in the minimization variable and concave in the maximization variable, then there are several famous minimax theorems, and one of them, the Sion's minimax theorem, tells us that the order of min and max is not important. So the min over theta hat and max over theta is the same as max over theta and min over theta hat for the convex-concave setting. Okay. And the optimal solution that actually achieves this minimax is called the Nash equilibrium. The pair theta hat and theta which gets this minimax is called the Nash equilibrium. And there are several efficient algorithms for this setting which query the gradients of the function L with respect to theta hat and with respect to theta, and then output the, and then try to approximate this Nash equilibrium efficiently. And some popular algorithms include gradient descent ascent. There are algorithms known as extra gradient methods, and then from the game theory literature, there are famous algorithms called fictitious play, and then there are also algorithms which are based on online learning. They are designed for different settings. For example, in general, if you are in a continuous setting where you are able to do gradient based algorithms, in the convex-concave setting, the continuous time optimization methods like these ones are usually what you would use. But maybe if this is actually being played out in real world, it's not about optimization, but rather it's in a game theory context, you might be using something else. Yeah. So all of this, so this these efficient algorithms are all, they all work for the convex-concave setting of the minimax optimization setting. Okay. But the problem that we encountered, even the simplest setting such as like Gaussian mean estimation does not fall into this setting. It turns out to be not convex-concave. And the main reason for that is, for example, if you look at this function, right, this is the function that we wish to do the minimax over. So if you look at it in terms of the parameter theta, so this should be concave here. So it's not, because we are trying to maximize with respect to theta, we would like this to be concave with respect to theta for us to be able to apply the previous results. And it's not because, I mean, once, this is already a square loss, and this is convex in theta and not concave in theta, and then there is an expectation over the samples, and the samples are being drawn from this distribution, so the overall dependence becomes much more complicated. So in general, this is not convex-concave, the minimax formulations that you write here. So the minimax theorem does not hold, but it turns out that you can do a simple extension of the minimax problem onto the space of probability distributions. So instead of requiring to find a single estimator theta hat, if you relax it to find a probability distribution over theta hat, or linear combination of the estimators. And similarly, instead of trying to find the maximum over theta, if you are allowed to take a maximum over the probability distributions on theta, then what you have here is again an expected value of over P and Q, and where P and Q are probability distributions respectively over theta hat and theta, then this becomes bilinear, okay, on the probability space. Because expectation is just linear in the underlying probability things, right? So this becomes bilinear, and once this is bilinear, this is also convex-concave, and now the minimax theorem holds. But the only difference is that earlier you would have liked to find a particular theta hat and a particular theta, but once you do this, you will be able to find only a distribution over theta hat and a distribution over theta, okay? The distribution in terms of theta hat is not bad for us because a combination of estimators is still again an estimator, okay? But so in our setting, it's not particularly bad, and this is totally fine for us to actually find. But in general, these things may not be the same when you go from, so originally when you wanted theta hat and theta, that's called a pure Nash equilibrium. And once you go to these probability spaces, it's called a mixed Nash equilibrium because you don't have a single point, but you actually have a distribution over multiple things, okay? But in our case, as we mentioned, a distribution or linear combination of estimators is still an estimator. So we are totally happy to have this probability distribution here, and so we are okay to solve this problem. Okay. Okay. So now that this is convex-concave, this is bilinear and so convex-concave, can we directly apply the standard convex-concave minimax algorithms? And it turns out that it's not obvious because the resulting spaces that we have here now are infinite dimensional, because we are looking at probability distributions. So gradient algorithms are not directly applicable here because the gradients themselves are infinite dimensional. So you may want to do some kind of stochastic method where which overcomes the issue that the gradients are infinite dimensional and so on, but even this extension is not obvious. So the one feasible approach that we pursue in this line would be through online learning. And the one thing that I want to mention at this point is that while convex-concave games go through convex online learning, because the underlying function L is not convex in theta hat and theta, okay, we will end up having to do some kind of non-convex online learning, okay, and that's what we'll focus in the rest of this talk. Yeah, so the Minimax theorem does not really have anything to do with computation. It only tells you that Minimax is equal to maximin. That's the only thing it tells. But in some sense, to me, that's kind of indicative of whether you can solve the problem efficiently or not. For example, this problem, at least in some cases, I'm able to tell you, okay, so the Minimax theorem holding or not holding is perhaps not super important at this point, but the fact is you can actually find the solution to this, but you may not be able to find solution to the pure strategy. Yeah, so Minimax theorem holding or not holding is only indicative of whether something seems solvable or not, but that's not really important here. Yeah, I'm not relying on that. Okay, so as I mentioned here, so the one feasible approach that we'll pursue in trying to solve these kind of problems here is using online learning, and because the function here that we are doing is not convex concave, we will have to rely on non-convex online learning. So in the first part, I'll broadly talk about how to do non-convex online learning, and for this part, let's just forget about the Minimax problem. Let's just focus on how to solve the non-convex online learning thing, and then I'll connect it to how to use this in order to solve the Minimax optimization. Okay. So let me now just focus on online learning. So let me briefly motivate. So online learning is useful and interesting in its own right. So let me first motivate what online learning is. So let's say we are like a group of policemen, and we are in charge of securing, say, 5 different places. And every night, maybe a robber attacks one of these places. And however, we would like to go to patrol to these places, and unfortunately, we can maybe go to only one of these places. So the question is, every night, where do I patrol? And maybe the robber is adversarial and he's calculating. So we cannot expect that he acts in a way that we think is natural or stochastic or anything. So the question that as a group of policemen we need to answer is, which of these 5 places do we need to go for patrolling, right? And a second example would be, say, portfolio selection. Say I have 100 rupees that I get every month, and then I have 3 options in these 3 stocks, and then I want to determine which stock do I invest in. And if I don't know too much about the financial markets and so on, when I'm going to invest, I don't really know which one is going to work in which way. But only at the end of the day, I'll figure out, I'll see how each of them has performed, and then the next month I have to take the same decision again. Okay. So broadly, online learning corresponds to taking such decisions under uncertainty, where I need to take a decision. Here, it's about investing in which stock, and in the previous one, it was about patrolling in which place. However, I don't really know until something actually happens whether which of these stocks is the best performing, or in the previous case where the robber might attack. Okay. So online learning tries to solve these kind of problems. So formally, we have, say, discrete time steps 1 to t, and at time t, we need to take this action or predict xt in some set x, script x, and after playing the xt or taking this decision, we observe the corresponding loss function lt, and our goal is to minimize the cumulative loss of lt of xt. Okay. This is broadly the goal. So let me just try to illustrate how this fits in with the examples that we saw. So here, xt would be the indicator vector of no patrolling. So here, if I'm going to patrol in this first place, then I'll put 1 for all of these other places, right? And the cost here is indicator vector of the thief. So if the robber happens to strike at a place where I'm not going for the patrol, then the loss is just the inner product between the 2 vectors. Okay. So xt is my action where I'm going for patrolling. Okay. And in the portfolio selection, the xt would be the indicator of where I'm going to invest, and the cost function would be the negative yield of different venues, so negative of this. And so the loss I'm incurring is just the inner product of the yield with the actions that I'm taking. Okay. And in both of these cases, I would like to minimize the cumulative loss, which is summation t equal to 1 to t LT of xt. Okay. For simplicity, in the current talk, we'll just assume that LT is fixed ahead of time. It's just that we don't know LT. It's already fixed ahead of time. But that could be worst case depending on our strategy. So LT would perhaps know our strategy, but that would be fixed ahead of time. Whatever result I say here can be extended using standard results for the case where LT can be adaptive. So LT can depend on all my actions so far and also the action that I'm going to take. Okay. So the results in the setting can be extended to the setting where LT can be adaptive. Okay. So the goal, as I said, is to minimize this cumulative loss. Now, when I say minimize this cumulative loss, we need to have a benchmark with which we are comparing this quantity. Okay. So the best benchmark we would think is to minimize, have an x star of x star t, which is optimum with respect to LT, right? So the best possible benchmark I could hope for is that I'm comparing with, that I can compare with is where my action at time t is the best thing that could happen for the loss function that I'm seeing at that time. But it turns out that this is way too hard, and in general, it's not possible to do this. So the benchmark that is considered in this context is you fix the action which is best in hindsight. So let's say I give you the entire sequence, all the losses. I tell you that this is how all the stocks are going to behave, and then I am allowed to pick a investment strategy which is constant for all the times. I am not allowed to vary the investment strategies. And the difference between my loss, where I have taken this action, and this benchmark where I'm minimizing with respect to a constant action, is called the regret of the algorithm that I'm using here. Okay. And it turns out that having a so I'm summing t terms here, right? As long as I have a vanishing regret, as long as this regret is little of t, it grows smaller than t, it turns out that I can use this to solve the minimax problem. Okay. So all I really care about is getting a algorithm which has vanishing regret in this context. Okay. Yeah. Yeah, you still get sublinear regret. So when I say adaptive, what LT knows is everything except your randomness. So for example, in XT, I'll be outputting something from some distribution. The loss function can know the distribution, but it may not know the exact sample that I'm going to draw from the distribution. So it's adaptive against those kind of adversaries. Okay, so this is a framework of online learning, and in the framework of online learning, we are interested in regret minimization algorithms. This again has a very rich history going back all the way up to Brown and von Neumann in 1950. And one of the first settings that were considered was online linear learning, where the loss function LT here is linear. So you have a vector CT, and each LT of XT is just inner product of CT comma XT. Okay? And the general setting of online convex learning is much more recent, but by now is again, it's been very widely studied. And it turns out that in both of these cases, we know of algorithms under some assumptions, of course, on LT and XT and so on, that we can get a regret which scales only as square root t. So this is in particular like little of t. So we have a vanishing regret here. Okay? And it also turns out that the square root t is tight. You cannot get a regret which is better than square root t. So in our case, we want to extend these kind of results to the case when LT is non-convex. So the most general thing here that we can have is for convex setting, where we have this kind of regret. And the question that we would like to ask here is whether we can extend this regret rate even to the non-convex setting, where each of these LTs could be non-convex. Without any further help, this turns out to be computationally intractable, because even if I tell you all the loss functions ahead of time, or at least a distribution of what the loss functions are going to be, this the special case would be non-convex optimization, and we already know that non-convex optimization is already NP hard. So without any further help, we cannot really do anything. So people have considered broadly two different alternatives. So the first one is weaker notions of regret, which is similar to say first order stationarity and optimization, where you don't ask for local optimality or global optimality, but you only ask for maybe gradient equal to 0 kind of points. Okay? But this is not very helpful in designing minimax estimators because this does not really tell you anything about the optimality of the point. It only tells you that the gradient is equal to 0. The second kind of results, which started actually, which is very recent from this paper last year by Agarwal, Gonin and Hassan, basically assumes access to optimization oracles of a certain kind. So let's say LT are not convex, but they are somehow easy to optimize. Okay? Then all you are left with in this question is, can you design these offline optimization oracles? Can use these offline optimization oracles to actually do online learning. And that's the approach that this paper deals with, and that's the setting that we'll be looking at. Yeah. No, you cannot optimize Lipschitz functions. That'll take exponential amount of time. When I say optimize, I want like at least polynomial time algorithms. No, even then it cannot. It will take exponential amount of time in the dimension. Like for example, MaxCut or any of the simple problems, they all turn out to be NP hard. I mean, we can discuss offline. Yeah, so we'll be working in this framework where we will first assume access to certain optimization oracles and see how to do non-convex online learning, and then we'll go to the next part. Okay, so in this setting, the main result is as follows. So these are the only two assumptions. So the first one is that LT is Lipschitz continuous, and I'm making this assumption, but even here, optimization is not easy. And so I have to assume that I can do optimization efficiently. And then xt lies in a set script x with bounded diameter. So these are the only two assumptions. Okay. And in this setting, our result basically says that you can actually get a regret rate of square root t, which we saw was tight even in the convex setting. And the breakthrough result of Agarwal, Gonin and Hassan was the first result in the setting, and they got t to the 2/3, and this can indeed be improved to the optimal square root t regret rate. Okay. So the main algorithm, okay, so at least the main intuition for the algorithm that we want to use in this setting is what is called the follow the leader. So the idea is this. So for any t less than or equal to t, we define as the leader x to be x2 t, which is the minimizer of the cumulative loss so far. Okay, this would be our comparator at time t, because this is our benchmark. And we do not know LT, right? So we cannot compute x2 t. So all we do is we can play xt equal to x2 t minus 1. So at t minus 1, so at time step t, we have seen all the loss functions till t minus 1. We'll compute the empirical minimizer of the cumulative loss till t minus 1, and then we'll play that as our strategy at time step t. This is called follow the leader because x2 t is the leader at time step t, and because we cannot output x2 t, we are just outputting x2 t minus 1. Yeah, so here we are assuming that the whole loss function is revealed. Yeah, and then that's why we are able to do this minimization. There are also weaker oracle models where I only give you function evaluation at some point. The non-convex things have not been studied in those settings. Yeah. Okay, so this is follow the leader algorithm, and it turns out that this actually performs pretty poorly, even for a simple example. So let's say we have a one-dimensional set -1 to 1. The first loss is x, and then the losses alternate between minus and plus. Okay, so just to give an intuition, so L1 of x is equal to x. So in the second time step, what we'll choose is a minimizer of this function, right? So we'll choose -1. So we'll choose -1. Right. So this is the cumulative loss, right? When t is equal to 2, this would be the cumulative loss. So I'll pick -1 to be my minimizer, and the next time it turns out that this actually has highest loss. And when I go to the next time step, the cumulative loss just reverses, and then I'll pick 1, and then it turns out that this has the highest loss. So this basically continues, and it turns out that in this case, it's easy to show that the follow the leader algorithm has a regret of omega of t. And the main reason for this is that my algorithm is totally oscillating between two extremes of the endpoint, and every time the adversary is just picking something which maximizes the current error, and then in the next time step, I would think that something else is, and then it's just oscillating. Okay. So the follow the leader algorithm that we just saw performs pretty poorly even on this simple example and has omega of t regret. It's not vanishing regret at all. However, a simple modification, which is perturbation, the algorithm is called follow the perturbed leader. Turns out it does much better and has a regret of O of square root t. The idea behind this is very simple. You pick a random vector each of whose coordinate is uniformly distributed between 0 and square root t. Okay. Instead of picking the loss, instead of minimizing just the empirical loss so far, the cumulative loss so far, you also add this random term. Okay. And this randomness, so we recall that the loss functions are fixed in advance. So this randomness is independent of the loss functions that were fixed in advance. Okay. So instead of just choosing the minimizer of the cumulative loss function till now, I'll just add a random part to the cumulative loss function, and then I pick the minimizer of the resulting thing. Okay. This is the algorithm. This is called follow the perturbed leader, and it turns out that it has a regret of O of square root t. So in this case, when I'm fixing all the LIs beforehand, I don't have to use independent randomness. If I am using, if my LI could be adaptive, then I will have to use independent randomness. But the algorithm, like this regret rate, it doesn't matter whether you use independent randomness or
sigma picked once or it's picked once at each time?
When LI is fixed ahead of time, sigma can be fixed, picked once and fixed ahead of time. When LI is adaptive, you have to pick every time independently. Yeah. LI is just Lipschitz. It could be in whatever range. LI is 1 Lipschitz. It does not matter. I mean, like all the LIs you could just translate, right? You could as well assume that it has a mean 0 or something. You're minimizing over the entire set, so adding a constant does not really change the minimizer. Sorry?
I'm saying when you go sigma, it's not scaled with the LI.
So it will scale with the Lipschitz constant of Li.
Yeah.
Yeah, it will scale with the Lipschitz constant of Li.
So this is why I was saying the one.
Yeah, so Li, I'm assuming that it's 1 Lipschitz,
Okay.
and then sigma has this thing, and then there is a relation between Lipschitz constant of this and how I choose this. Yeah. What's the question?
How reasonable it is to assume that all of LIs will be? You said you're assuming that.
Yeah, so it depends. So in some of the applications, for example, so we are still able to use this in minimax estimation. So in some settings, it's not too bad. Also, for example, you could think of this Li as, in the machine learning context, you could think of it as a perturbation, right? Once I give you a perturbed data point, you could do whatever with that perturbed data point. So even though it seems like there is no way for me to get a full function, it's basically I'm giving a perturbed data point, and then there is some loss on that perturbed data point. So it's not unreasonable in some settings, at least. Yeah. Like the algorithm right now needs it, at least an upper bound, and then your bounds will depend on an upper bound. So as long as you are at least able to estimate an upper bound on the Lipschitz constant. And maybe like there are also some intermediate results that we can say about how the iterates xt should be. So if your assumption is violated, you may be able to figure that out. So the main intuition behind why this follow the perturbed leader gets a regret of O of square root t, like there are two parts. So the first one is what is called be the leader lemma. This basically says that if I am indeed able to play xt plus 1, right? Xt plus 1 is the cumulative loss all the way up to time t, and then this perturbation. Because this perturbation is only of square root t, then if I'm able to play the leader at time t plus 1, then the regret is at most square root t. And the square root t is just because sigma is of the order of square root t. Okay? So if sigma was smaller, if sigma was equal to 0, then this would actually be, there will not be any regret. Okay? But the issue is I cannot actually run this algorithm because this requires me to play xt plus 1. Okay? This requires me the knowledge of LT, which I don't have at this point, so I cannot play xt plus 1. So I'll do the perturbed leader, which actually plays xt instead of xt plus 1. The second lemma basically says that because you're adding some amount of sigma here, there is stability in your write rates, meaning that the xt's and xt plus 1s do not really, okay, so let me move it. So because LTs are Lipschitz here, the loss difference between xt and xt plus 1 is directly limited by L, which is a Lipschitz constant, times the distance between xt and xt plus 1, right? Because I'm adding a sigma in the optimization here, what I'll be able to show is that if sigma is very large, then this perhaps dominates this term, and the xt and xt plus 1 are essentially the same, right? So there is a sweet spot that I'm taking here. So sigma equal to 0 would be best here, but then I actually cannot implement this algorithm. So I'm implementing xt, but this is xt is close to xt plus 1 when sigma is large. So sigma equal to square root t seems to be the right trade-off between both of these, so that one, be the leader gets a good regret, and two, follow the perturbed leader actually gets the same regret as be the leader. Okay. So let me go a little bit more into this stability analysis. So the main question, as this inequality points out, is I want to bound the expected difference between xt and xt plus 1. I want to be able to say that no matter how LTs are chosen, as long as they are Lipschitz, xt minus xt plus 1 will not be too large. And the previous best known result for this was t to the minus 1 over 3 by Agarwal, Gonin, and Hassan. And we were able to improve it to 1 over square root t, which basically gives you the square root t regret instead of the t to the 2 over 3 in the previous paper. Let me give you a brief intuition of how one does this in the linear case from Kalai and Vempala's original paper. So in the linear case, Li of x is the inner product between a vector Ci and x. Li is Lipschitz is the same as saying that Ci is a bounded vector. Okay, the norm of Ci is bounded. It's the same as the Lipschitz constant. And once we take sigma to be uniform in 0 to square root t, we see that the optimization problem that we have here, so the cumulative loss plus sigma, is the same as a linear optimization, where instead of summation Ci, I have sigma plus summation Ci. Okay. Now, the difference between xt and xt plus 1 is only in the functions that are being optimized in both the cases, right? So in one case, I'm optimizing sigma plus summation I equal to 1 to t minus 1 Ci. In the other case, I'm optimizing sigma plus summation I equal to 1 to t Ci. So the only difference between these two is Ct. Okay, and once you fix these Ci's, if you choose, because sigma is being chosen randomly with each coordinate be uniformly between 0 and square root t, the whole random vector here lies in a box where this point corresponds to, say, this vector, right? So sigma lies uniformly in a box. That's how I'm sampling sigma, and I'm adding sigma to this fixed vector. So the resulting distribution would be again in a box where one of the corners corresponds to this this vector, and this box would be this vector. Okay, so one would be this and one would be this, and the distance between these two is just Ct. That's the difference between these 2 points. Okay, while the size of these boxes is actually square root t. So most of the box actually overlaps with each other. The only amount of the probability that's present in, or the volume of the symmetric difference between these boxes is only of order 1 over square root t, because the whole box is of size square root t. Okay, the relative volume is of order only 1 over square root t. Okay, so this is the linear case, and from here it's also very clear that it's totally unclear how to extend this to non-convex case, because this box thing is true only for the when we have these linear functions, because we are able to write it as inner products. But when this is non-convex, then adding sigma here or adding some other function here we can no longer use this kind of argument. Okay? And in that case, it turns out that we have to develop some kind of monotonicity properties, and maybe in the interest of time, I'll skip the proof of this part. Just to recap the first part that we have here. So we looked at follow the perturbed leader algorithm for non-convex online learning, and we saw that we can use the be the leader lemma and stability arguments to say that follow the perturbed leader actually gets 1 over square root t regret rate for non-convex online learning. And the key technical results were some tight monotonicity lemmas. So one thing I had to mention, which I haven't fully mentioned, is that how am I able to overcome the non-convex part? So the reason is that I'm assuming that I'm able to implement this algorithm, right? Follow the perturbed leader requires me to solve this minimization problem. And here, because Li is convex, I don't have a polynomial time algorithm always to solve these kind of problems. But I'm assuming access to those oracles. Assuming I'm able to implement the follow the perturbed leader algorithm, then whatever I told you is true. But implementing the algorithm may not always be obvious because this involves non-convex optimization. Okay? And when we go to the application, one of the example applications that I'll mention, I'll describe how to solve these kind of non-convex optimization problems arising in that particular setting. So let's look at how we can use this online learning to actually do minimax estimation. So as we saw, we have this minimax estimation where we are minimizing over probabilities in theta hat, and this again maximizing over, say, either probabilities or exact does not matter here, because like the optimum is always achieved at one of the corners. Okay, and then this is the function that we are looking at, expected value of p of theta hat of L of theta hat comma theta. So there are two players here. One is the theta hat player, which is the estimator, and the other one is the max player, which is the choosing the worst case parameter distribution. Okay, they are in some sense interchangeable because of the minimax theorem, so we can do either minimax or maxmin. So in this case, we can apply, so the theta hat player plays a regret minimization algorithm. In this case, we will play FTPL because we saw that FTPL is a regret minimization algorithm. Okay, and the theta player, the maximizing player, will play best response. Okay, let me try to describe what this means. So the theta hat player will first come up with some probability distribution, some estimator, which is P0 of theta hat. Okay, the theta player will look at this P0 of theta hat and then try to find the max over the worst case probability distribution that maximizes the risk. So this is called the expected risk of this estimator. So first, we get an estimator, and then I'll choose a parameter which gets the worst risk for this estimator. Okay. In the next step, the estimator is given by the follow the perturbed leader algorithm when I'm given this particular, the samples drawn from theta 0. Okay, and then theta 1 is again best response, meaning that it again picks the maximum with respect to P1. So we had P0 here, theta 0 is the max for P0. P1 did a FTPL on theta 0, okay, and theta 1 is a maximizer over P1. And then P2 is FTPL by taking theta 0 and theta 1. And then theta 2 is maximizer for P2. Yeah. Yeah, so the way I'll implement it is actually I'll use the regret minimization algorithm on this one. And okay, so firstly, because the minimax theorem holds, I can interchange the min and the max. And so the way I'll eventually implement it is going to be the opposite of what I'm saying here.
No. How do you compute?
So, okay, so let me give you, okay, so I don't really explicitly need to compute P1. all I need P1 for is to be able to do this thing, right? And for this, I have an expectation over something. As long as I'm able to sample from P1, I can try to compute this theta1. The only reason I need P1 is to be able to compute theta1. That's where it comes in, right? So as long as I'm able to sample from P1, I'll compute enough samples so that this true expectation is approximately equivalent to the empirical expectation, and then I'll solve this maximization problem. That's how I'm going to implement. Yeah, so because even if you put a maximization over the entire distribution, the maximum will be achieved at some point. So let me come to the example. It will be slightly different. Yeah.
Take a few more minutes.
Okay. Okay. So again, let me try to briefly sketch why the fact that regret minimization plus best response can actually give you minimax solutions. Okay. Okay. So here I haven't told you. So the final output is an average of all the probability distributions I have here. And again, I will not represent the probability distributions explicitly, but I have this from which I can sample. Okay? And once I have enough samples, then I can get a discrete approximation of the true underlying distribution. Okay. So the final output that I'm going to give is an average of all the distributions I have throughout my algorithm here. And why is this going to be minimax optimal? Because first let's look at the maximum risk of this distribution. Okay, so I have 1 over t summation t, this expectation, and then I'm taking a max over all parameters. So this is the maximum risk of this estimator. This is less than or equal to the what I get by replacing each theta with theta t, because this was the best response. Because for each pt of theta hat, theta here is less than or equal to pt of theta hat theta t, because theta t is the best response for every fixed pt. Okay. Now I know that the strategy that I'm playing, which is this pt of theta hat, is has a regret guarantee of 1 over square root t, because I'm taking average here. So square root t over t is 1 over square root t. So this is best. This is almost as good as using a fixed probability distributions for all the steps here. Okay. So I have this min over p theta hat here, and this is trivially so because I'm using the same probability distribution here, replacing this theta t with the maximum over theta is strictly is at least as large as this one. So what this says is that the worst case risk of the estimator that I have here, this is the average, is less than or equal to the minimum risk achievable by any of the estimators here. And this basically is a two-step argument which uses both the best response of one player and the regret guarantee that the other player has against the best response. Okay. And historically, this is not the so this argument is not new. This has been known at least since Freund and Shapir's '96 paper. The main new development, however, is we did not know of regret minimization algorithm for the non-convex setting, and this is the recent development that we can use in combination with this earlier approach. However, as I mentioned, the main challenge is to actually implement the FTPL algorithm and in particular solve the associated non-convex problems. And if we contrast this with other related works which do minimax estimation, classical minimax estimation in the statistical literature, they end up guessing one side of the mixed strategy, but this guessing is not a easy algorithmic process, and this can be like these kind of results are known only for very, very special cases, and it's usually not clear how to extend. Whereas the approach that we have presented here is pretty much fairly general, but implementing it might be challenging in many scenarios. Okay. So I just have 2 more slides and I'll finish. So let's now come back to the Gaussian mean estimation setting, where we want to implement this approach to estimate the Gaussian mean from a given number of samples. So let's say we are given x1 to xn from standard normal distribution with mean theta and covariance matrix identity. Theta is in d dimensions, and let's say theta is in a ball of radius b, okay, and the goal is to estimate theta. The Minimax problem is just written here, and just for sake of simplicity, we write the risk as R of theta hat comma theta. Theta hat is the estimator and theta is the parameter. Even for the special case of n equal to 1, which I mentioned in the beginning, there are several works, but we don't know of a Minimax estimator when the size of the ball is greater than this constant 1.16 times square root t. Okay. Estimating the mean of a Gaussian, the Minimax estimator for the mean of a Gaussian with a single sample is unknown whenever the size of the ball is greater than or equal to this constant times square root t, where d is the dimension. Okay. At least for this particular case, our work resolves this question in the sense that we are not able to give like closed form expressions for the Minimax estimators, but we are giving an algorithmic procedure to compute these Minimax estimators. Okay. So there are two key steps. So the first one is symmetry. What it does is it replaces the maximum over ball of size b to a one-dimensional problem, because there is a result by Berry which says that the worst case risk is achieved by uniform distribution on the sphere, and the only thing we don't know about the this sphere is its radius. So we can reduce the whole d-dimensional problem into just one-dimensional problem, because once we figure out the radius, it will just be uniform distribution on the sphere. The worst case risk is achieved by something which is uniform distribution on the sphere. And when we are implementing the FTPL algorithm, there are two problems that we need to solve. So the first one is a maximization problem. So this is precisely the maximization problem that arises in the follow the perturbed leader, where sigma is this perturbation. Okay. However, it turns out that while this is non-convex, it's only one-dimensional. So we can just do a grid search on this one-dimensional space, and it does not really blow up in the dimension. The second kind of problem, this is the best response problem that corresponds to the best response, and the problem that we have here turns out to be that we need to compute Bayesian estimator, a Bayesian Minimax estimator for a symmetric prior, because we are getting spherically symmetric priors. So whatever probabilities that we have here will be again spherically symmetric, and this has been studied in the Bayesian estimation community, and we know efficient algorithms to compute Bayesian estimators for symmetric priors. So this is non-convex but one-dimensional. This is also not convex, but people have already shown how to solve this problem in the Bayesian statistics community. Okay. So to conclude my talk, I would just like to point out that Minimax estimation is a fundamental problem in statistics, and so far most results have been obtained through for specific problems using problem-specific intuitions and so on. And in our work, we present a general approach through non-convex online learning. The general approach was kind of already known, but the fact that this can be implemented even in a non-convex setting was unknown, and the main technical workhorse that we can use here is that we now know of efficient algorithm for non-convex online learning whenever we have access to certain kind of optimization oracles. And at least for some cases, we are able to efficiently implement this approach and obtain Minimax estimators that were not known earlier. That's all I had. Thank you. Sorry for going over time.